Welcome everyone to Module 3 of the Global Professional Fellowship in Green Urban Innovation and Entrepreneurship. I know we had a bit of a glitch, so we are going to go through this opening very quickly and just want to say thank you for joining us and many thanks to our speakers. We have carbon literacy and global impact is our topic, and these will be our key takeaways and what you will learn, as well as just making sure that you end up with actions. Everyone just take one moment of silence to give kindness, strength, and peace and love. And extend that to our speakers. And friendly reminders, please share your location. I know you might have already done that, and also ask questions. When you ask questions, make sure that you put the speaker for whom you're asking the questions for, and reminder that this is a space for uplifting dialogue. And look at all of the people around the world that are engaging in this program. Please do share. And I'm going to pass it over to you, Dr. Wissam.
Thank you so much, Michelle. So we start with our first speaker, Dr. Morgish. He's an associate professor at GCT College of Engineering and Technology in India. So the floor is yours, Dr. Morgish, and then you have 15 minutes, please.
Okay, sir, sure. Good morning, good afternoon, then good evening to one and all present here. First of all, I thanks to Dr. Sim sir and Mitchell for the brief explanation about this program. And my presentation is Unwavering Heat and CO2 in Steel and Cement, which is exploring the sustainable alternatives. So, first of all, what we have to know is what is being the unveiling. Unveiling is nothing but to show something new to the public for the first time. Why we are saying this unveiling is the first time we are showing this? Yes, we all know that steel and cement are the two eyes of our construction industries, but we don't know about how it emits the carbon dioxide. Okay, before construction of the construction itself, the steel and cement start to emit carbon dioxide. So my presentation is based on understanding of carbon emission in the construction sector, how the carbon is emission and how the construction sector plays a vital role in emission of carbon. Then what are the hidden carbon dioxide in the construction sector? Then what are the alternative sustainable materials we are using to reduce the carbon from net zero? Then what are the transition we have to follow and how to formulate for a low carbon development? So for the section one, I have to say that understanding carbon emission fundamentals. So normally we know the carbons are emission from various energy, from industrial areas, from many factories, then from the transportations, and especially in the construction materials also. Uh, Steel and cement is one of the plays a vital role in the emission of carbon. Okay, understanding these sources, okay, I am understanding the steel and cement is one of the sources of emitting carbon. What are the measurements I have to go? Or what are the environmental impact of carbon due to steel and the cement? What are the key concepts I have to follow? What are the frameworks I have to follow? So we are seeing this all the things in the forthcoming presentation. So normally, first, the carbon is classified into two types in the construction field. That is embodied carbon and operational carbon. The embodied carbon is started before the construction work. Though I say it is started 20 to 30 percentage of emission of carbon before we are going to construction. How? By the manufacturing of steel and cement. We are well know that for manufacturing of steel, we need blast furnaces of 1400 degree centigrade. By due to heavy high temperature, normally the carbon will emit. For manufacturing of cement, the clinker we are using it is the calcination. While heating this calcination, automatically the temperature will rises. So first of all, by the extraction and the manufacturing, normally the carbon is emission. Then after that, it is transporting and it comes to the construction phase. So normally this process will have a chance to emit 20 to 30 percentage of carbon in the construction field in the global environment. So how it is measured? It is measured in the kilograms of carbon dioxide for the standardized comparison and also for the tracking purposes we are using this measurement standards. So what are the regulatory landscape we are using? We have to adopt some code books to prevent this 20 to 30 percentage of carbon pollution in the global environment. I already said there are two types of carbon. One is embodied, other one is operational carbon. So embodied carbon is a pre-phase of building construction. Operation carbon is after the construction, we are using AC, that is air conditioner, heating by heaters, then electricity and water throughout its lifespan. So it is the most dangerous thing of emitting carbon in the global environment. So normally the embodied carbon is releasing 20 to 30 percentage only, but in operational carbon, nearly 70 to 80 percentage of carbon is emission. So it is most dangerous one in the environment. So how can we prevent this, both embodied and also the operational one? Here, when we are using the renewable energy sources, automatically the operational sources, operational carbon will get reduces. So what is the renewable energy? Instead of we are using the electricity, we can go for the solar panels. Then instead of for steel construction, we can go for the timber construction. So these are the some remedial measurements we have to switch over to reduce the carbon emission. So the manufacturing of carbon, there is the operational carbon. What is how it's different? So embedded carbon is very much less when comparing to the operational carbon. So here the embedded carbon is nothing but 20 to 30 percentage, but operational carbon is a lifetime of the building. It's not that lifetime of the building is nearly 40 to 50 years. This operational carbon footprint should be polluted our environment by emission of carbon emission. So these two things we have to watch very carefully and we have to take a necessary action. Otherwise, the carbon is emission day by day because we can't be able to control our steel productions or cement productions because day by day it will be increases. So I show how much it will be increased day by day and how much tons there increases. So my section two is depends upon the hidden carbon in steel and cement. I already said that it is a unveiled. Unveiled is the first time I'm showing to the society. That is the meaning. So how the steel and cement will produce a large impact as a carbon footprint in the construction projects. So here, first one is that is extraction of steel. That's we are getting from the iron ores, then from the calcinations, then manufacturing, then we are transferring from one place to other place. That is transportation. So these things started from embodied carbon, then it ends in the operational carbon. That is building. We are constructing these things, these building materials with steel and cement for the operational carbon. So this is the heavy cost of steel production and how the carbon dioxide is emitted. See, day by day it is always increasing. So I say that embodied carbon we have to manufacturing the steel. First we have for mining 10%, then it should be melting 70%, then we have to transport 15%, so other 5%. So day by day it is emitting a carbon of 2.6 billion tons CO2 annually. So both the embodied and also the operational, both combination, it creates nearly 14 to 20% as a US standard report. Okay, normally it produces 20% in the greenhouse gas effect. So from the production, normally CO2 emission is 0.15 to 0.35 tons. Then for transportation, it will take 5 to 15% of emission. Then the construction side is total volume should be 15,000 to 25,000 tons of concrete. We have emitting 2,250 to 8,750 tons of carbon dioxide. Look up this. Okay, so the main thing is both the embedded and the operational carbon. We have to make it as zero. So one of the things we have to follow. So to make it as zero carbon, we have to use for the alternative materials. But in as a traditional one, have little bit confusing about whether we have to replace steel or we have to replace cement, whether it will be give high strength and high durability, or whether it will be fail its strength or its durability. Because the any person have an idea. I have no idea about using the sustainable materials because they are just fearing about the strength and durability. Because strength and durability are the main important properties of concrete. So we are using here hempcrete. So it is a bio-based invention. It is a waste material. That is hemp fiber. We are mixing with lime binder. Lime binder means it's a calcium because we know that cement is very much rich in the calcium oxide. So it is chemical properties is 60 to 70% of calcium oxide. So the main thing ingredients in the calcium is lime. Okay, so lime binder plus water. While we are mixing, we are making as a alternative material for carbon. So due to this, the carbon segregation will make us carbon negative because hemp fiber have a capability to break the carbon and it will absorb the carbon from the atmosphere. So while absorbing the carbon, automatically it will break the carbon into pieces and it make it as net zero one. So this bio-based innovation makes a plays a vital role in the forthcoming case. So it is used mostly at present. It is used as a non-loading bearing valve. So this is the traditional mix. We are using 100% ordinary Portland cement. Due to this ordinary Portland cement, nearly 14 to 16 percentage of carbon is emission. So we are going for alternative material. Just we are replacing 50 percentage with supplementary cementitious materials. Nowadays, I say it's a hempcrete. We can use water hyacinth plant also because the water hyacinth plant have 23 percentage of calcium oxide. We can use that also. Then rice husk, then baggage, as so many things are there to replace cement at present nowadays. So, but we have to give assurance by replacing these materials, the strength and durability should be good and it should be high when comparing to the standard mix. By using this green concrete materials, normally the cost will be 5 to 15 percentage will be reduced, and also the carbon dioxide will reduce in the global house. So these are the some of the materials, sustainable materials we can use. There is cross-laminated timber, mycelium composites, rammed earth, recycled steel. Because when we are going to production of steel, we already say that it will cost of that is it will emit nearly 14 to 16 percentage of carbon. So when you are using the recycled steel, we can decrease the manufacturing of steel for 5 to 15 percentage. So when we can use for engineered bamboo, then recycled plastic. So these are the sustainable materials at present they are using to reduce the low carbon as a as a percentage. So how it will be transferred? When I am going to say, sir, I am going to use sustainable materials instead of steel and carbon, then no one came to me. How it is possible? Then some of them fear. Okay, the building should be very good high strength, or it should be a durability, or it should be undergoes failure in the earthquake. So I have to translate my strategy and I have to implement this to the society. How I will implement. First of all, I have to audit. I have to fix that. I have to say, see, this product should not affect the environment. Okay, some of them also agreed. Okay, you can go and audit. Then some of the persons have to analyze whether it should be have a very good high strength and whether it should be a net zero carbon. Then whether it should be have a durability. So I have to prove that. So after this analysis, I go for the specification. So I have to say that this a percentage of carbon materials we are using here is little bit decreased as the conventional one. That is 5 to 15 percentage of amount will be reduced. So I have to specify. Then I have to procure some suppliers because this sustainable materials I have to procure by some suppliers. After the suppliers should verify, okay, this product is very good. So this by the third party verification, I have to implement to the concerned society. So after this, I have to say the policy. See here, the one cement price rate is nearly 500 rupees per bag, but my product is almost 300 rupees, and also it will be very net zero one. So there should not be no carbon emission. I have to prove that. I have to give the price mechanism to the concerned market. Then I have to go for the building code requirements, because when we are using this carbon steel channel, we are going for the IS code 456 for designing in India. So as per the sustainable materials, we have to produce some guidelines how to use this sustainable materials instead of steel and cement. Then I go for the supply chain transparency. So this while testing, I have to, if anyone came to how show it the strength, I have to show that. So my product will gives the 5% strength more than the traditional one. So that chain transparency should be there for the implement of any products, any sustainable products, because we are going to alternative the materials. Okay, then certificate integration. So any sustainable materials, we have to go for lead, brave, and well certification, because when we give a certification of lead, automatically all the consumers will believe our product is the best one, because it is a certified one for the sustainable materials. Then financing incentives. I already said it's a financing incentives when you are going for steel or cement. If the rate is 500, here our product is 300, means automatically if we have very good strength and we have the certificate, means automatically all the peoples will come and approach us. Then corporate commitments.
Sorry,
Without corporate
Doctor.
commitment,
You have 2 minutes, please. Two
yeah,
minutes.
okay, sure,
Two
sure.
minutes, please.
Without corporate commitment, we can't be able to do this. So this is the building design. That is foundation tire. Foundation tire is nothing but we have to reduce the load. Then we have to use the sustainable materials. Then we have to, after using the sustainable materials, we have to reduce the carbon content. So this is the uh, this is the final one. So this is the first quarter. We have split it into first quarter, second quarter, third quarter, and fourth quarter. So the first quarter I have to give a carbon baseline audit. Then second quarter I have to go for the material specification, because my carbon materials is well than the traditional one. The third quarter I have to expanding my applications regarding the strength and durability. The fourth one I have to go for the procurement of consumers. So being this task, I have reached nearly within 1 year or 2 years. I have implement my sustainable materials. So thank you for your passion, and thank you for your attention. Ashim sir, I will end my session.
Yeah, thank you so much, Dr. Murgush, for this interesting sharings. And now we are moving to the second speaker, Miss Srinanji. And Ms. Rinshi is Associate Vice President of the Technical Development at Global Network for Zero. So the floor is yours, Mr. Sri, and you have 15 minutes, please.
Absolutely. Thank you, Dr. Wissam, and Global Ambassadors of Sustainability. It's an honor to be here today. So let me quickly get into my presentation. I am going to be talking about something very, very critical, where it's not just about carbon literacy and material sciences, but I'm going to be walking you through the entire process of rethinking material decisions in the construction, in construction, right from the process of selection up until the contract as well. So let me start with something very simple. It's a personal story. When I was a child, my mother used to constantly remind me of a few things. Like she would say, switch off the lights when you leave the room, and keep your curtains open to ensure there's a lot of daylight coming in, and don't waste electricity and things like this. At that point of time, I really thought about this as something perhaps to, save money. But over time, these habits have stayed with me, and the more I've forayed in my career into sustainability, I now realize that it's something that it fits a larger picture, and we don't always realize how these operational aspects play a very key role when we talk about emissions or carbon. But what's also interesting is the fact that in sustainability, especially with respect to buildings, it's not just about what happens during the operations, but there's a bigger story behind it, right up into the even before you actually occupy or even start the construction of the building itself. So, like I was mentioning, today I'm going to be talking about sustainable buildings, and most of this discussion will revolve around energy efficiency. When we say sustainable buildings, we often talk about optimizing energy, improving the efficiency, reducing operational emissions associated with HVAC systems and all of that. But the question we really need to be asking ourselves is, are we looking at the complete picture? Because if we focus only on operations, we are actually looking at only a part of the entire life cycle, and that realization is what will shift the entire perspective, basically. So, where does the real carbon impact come from? Because the reality is a significant portion of a building's carbon emissions is already determined before the building even starts operations, right? Now, in many cases, studies have shown that around 70% or even more of the total life cycle emissions are locked in during the early stages of the building itself. So, what does this actually mean? It means that before a single light is switched on, before the air conditioning starts, and before occupants even enter the building, a large share of the emissions has already been released into the atmosphere. And these emissions come from the materials that are being used for the construction of the project itself. So, from extraction, manufacturing, transportation, and construction, if unless we focus on operational efficiency, we are addressing only the problem partially. So, how does this matter to any of us, right? So, this is not just a theoretical discussion, right? This is a very real this has very real implications for anyone involved in a project. So if you are a developer, this is something that could directly affect your ESG positioning, investor expectations, as well as your access to even green financing. And if, on the other end, if you are a consultant or let's say a designer, then carbon is no longer an abstract concept. It becomes a design parameter, just like cost or performance itself. And if you are, let's say if you're a contractor who's into procurement, then your material substitutions and decisions will suddenly carry a lot of carbon implications when we start talking about embodied emissions itself. At the other end of the spectrum, now if you are a manufacturer, right, then your transparency with respect to product data becomes a major competitive advantage. So when we talk about embodied emissions associated with materials, it's no more a niche topic today. It's what is becoming mainstream. Now, like I said, this has become even more critical today when we look at the scale of construction that's happening globally. We are building faster than ever before, and urbanization is accelerating. Infrastructure demand is growing, and with that, the demand for materials like cement, steel, aluminum, glass is also increasing significantly. Now, here's the challenge that we all see. Now, most of the emissions associated with these materials are not clearly visible to us. They are not something that you can see on site, and rather they are embedded in the product itself long before it reaches the project gate, which is why you would have understood from the presentation by the previous participant, Dr. Murugesh, where he says it's called embodied carbon because it's embedded into the entire process of the product itself, of the material itself. So naturally, the next question is, where does this carbon come from, right? It comes from multiple stages. It starts with the raw material extraction, as you could have seen in the previous presentation. There's mining, processing, and all of this involved. Then comes the entire manufacturing process itself, which is often very energy intensive and sometimes involves chemical reactions that releases emissions. And then, of course, there's this transportation, meaning the moving of materials that happens across regions and countries. Now, and finally, when the construction activities begin on site. So each of these steps adds to the entire carbon footprint. And when you add all of them together, the impact that each material has becomes extremely significant. Now, here's what happens, or rather, here's what makes this problem particularly challenging. From a traditional engineering perspective, we predominantly evaluate materials based on strength, on durability, and cost availability, of course. But carbon does not always align with these parameters. So let's take two materials. They could look exactly the same, they could perform the same, they may even cost the same, but their carbon footprint can be completely different. And unless, of course, we specifically measure it, we would never know the difference between these two materials. So let me explain this with a real example. In one project, there was a particular type of steel that was selected. And from a technical standpoint, everything was perfectly fine. It met all structural requirements. It complied with the specifications that was showcased. And there were no issues in terms of performance as well. But when we evaluated it from a carbon perspective, it did not meet the project's carbon targets. And why was this? It's purely because of the manufacturing process itself. So the steel was, produced using a blast furnace, which is, of course, as most of you might know, highly carbon intensive, and it also relied a lot on iron ore and coal. Now, if the same steel, let's say, had been sourced from an electric arc furnace, or where they had primarily used perhaps recycled steel and electricity, then the emissions would have been significantly lower. So technically, both options were acceptable, but environmentally speaking, they were very different. And that is exactly where the decision-making gap exists today when we talk about embodied emissions. Now, if we break this down into life cycle stages, most of this embodied carbon falls under what we call the A1 to A5 stages. A1 being the raw material supply, and then there's transportation, manufacturing, and A5 is related to the transportation and to the site and the construction itself. So these are the stages where most emissions are concentrated. So if we want to reduce the embodied emissions, this is where we will have to keep our focus on. So to understand the scale, right, let me give you a few indicative values. Cement typically emits around 0.85 to 0.95 tons of CO2 per ton, largely due to the calcination process. Then concrete emissions vary depending on the mix design, but can range, widely from about 0.4 tons per 0.4 tons for the electric furnace, up to about steel as well. And having said that, aluminum again is very energy intensive, but recycled aluminum can reduce emissions by about 95%. So these are not small differences. These are significant variations that can drastically impact a project's carbon footprint itself. So the important takeaway here is that we don't need to optimize everything at once. A large portion, almost 80 to 90% of embodied carbon in buildings comes from a few key materials, primarily your concrete, steel, aluminum, glass, and various facade systems as well. So if we focus our efforts on these materials, we can achieve substantial reductions. When we talk about embodied carbon, cement is one of the biggest contributors, like we've discussed in the previous presentation. And it's important to understand why. It's not just because of the energy use. In fact, a large portion of emissions from cement actually comes from the chemical processes itself during the clinker production. So I'm not going to be getting into much details about it because I think there was a large part of it that was already dealt with in the previous presentation. But it's important to understand the various aspects associated with the entire chemical process in the manufacturing of these products for us to understand the entire picture around the embodied emissions of these various materials. Similarly, we've got about with respect to steel. Now, this again is another very carbon intensive product. So from a design perspective, it meets strength requirements, structural performances, and all of that. But from a carbon perspective, there are two very different pathways, right? Like I said, one is a blast furnace route that could be taken and highly carbon intensive, and the other is where you use an electric arc furnace and things like that. So decisions in the entire process of manufacturing of these materials will have an impact on their carbon footprint. Aluminum is an interesting material here because it has one of the highest embodied carbon values among the common building materials, but also it's one of the highest potential. It has the highest potential for reduction itself, right? So this is again something that could be looked at in terms of materials for your buildings. So at this point, it's important to simplify the approach, right? Because when we talk about embodied carbon, it can feel very, very overwhelming. There are so many building materials involved. But the reality is that we don't need to be optimizing everything. A small group of materials that contribute to the majority of the emissions is what we will have to be addressing and make the right decisions moving forward. So now that we've understood where the emissions are coming from, the next step is about measurement, because without measurement, we are only making assumptions, and embodied carbon needs to be quantified. And today we have the tools that help us do that, right? We use life cycle assessment methodologies to calculate emissions across stages. And increasingly, this is becoming integrated into the project workflows. So instead of guessing which option is better, we can actually compare material databases and shift the decision making from just opinions to actual evidence-backed decisions. And to support this, we rely on several tools and standardized data. So your environmental product declarations, or EPDs as they are commonly known, are one of the most important components because an EPD provides you with the verified information about the environmental impact of the product itself. So like I said, instead of generic assumptions, we can use product specific data. Then of course we've got tools like EC3, one-click LCA, Athena. All of these help us aggregate and compare based on actual data. So these tools will allow us to run scenarios based on which decisions can be made. Right, so this is this gets really powerful. You'll be able to model scenarios based on the materials at a very early stage in the design itself to help you make actual decisions where you can change materials, you can optimize quantities, you can also explore alternate materials as well. And based on that carbon modeling, you'll be able to make actual decisions. So now that the design intent is already put into place, what's designed has to be translated into something that gets procured and ultimately constructed as well. That's going to be very, very critical. So how do we do that? We move from understanding the problem at the stage of design up into the implementation, right? So let's look at how we do that in practice. For example, let's start with concrete here. Now, instead of just specifying the strength, we could be going ahead and saying concrete should be emitting about less than 300 kgs CO2 per cubic meter, right? At this point, the question would then be, should this be M30 or M40 steel? But it's also important for us to understand what would be the carbon impact of that mix accordingly. So based on similar questions, it's important to float your tender documents, right? Where you have EPD backed BOQs that play a very key role in and help you in the actual decision making process. You should be able to make decisions based on transportation, meaning distances that are being transported, based on which you will also be able to understand the entire embodied emissions of the particular product. So it's all about
2 minutes. 2 minutes, please.
Yeah, absolutely. So once you've specified, and tendered for low carbon materials, all of this gets locked into your contracts and helps make the right decisions in terms of your supply chain and vendors from whom you're going to be able to purchase effective and efficient materials for your construction. So various things that you can check at the construction stage as well. Once you've floated your tender documents and purchased the associated materials, you have random global warming potential spot checks that can be done, and you can log the actual EPD databases of the products that are being delivered to the site. So all of this will be will play a very key role in the verification process during the construction phase. So stepping back a little from the project level, this is what it looks like on a global perspective, right? The world is changing today. Across nations, we have various aspects of carbon coming into the picture, especially with respect to embodied emissions. So some real example numbers that showcases how the world is seeing a reduction from the lens of carbon. And that's where it's going to be very critical I'm just bringing into what we do at my organization. So right from design into construction into operations, you would be required to quantify all of the emissions associated with each material, each process. And based on that, there's a verification or a validation that happens with certification of bodies like Global Network for Zero, which is what we do. And based on this entire approach of that's structured around your project, you'll be able to make the right decisions associated with embodied emissions. So after everything that I've said today, I want to leave you with one simple idea. Ask for the EPD before you ask for the price of the product, because the moment you do that, you can change the entire conversation. And today, most decisions are driven by cost first, and carbon becomes an afterthought. But when you ask for the EPD first, what you are basically saying is performance matters, impact matters, and transparency matters as well. So I'll leave you with that thought. And remember, every material that we choose builds the world our children are going to be living in. Thank you so much for the time today. Would be happy to take any questions that I might have at the end of the session.
Yeah, thank you so much, Ms. Sri, for this interesting presentation. And now we'll move to the next speaker, Prof. Dr. Muhammad Fazil bin Arshad. And Dr. Fazil, Prof. Fazil, he is the director of the Institute for Infrastructure, Engineering and Sustainable Management at University of Technology Mara in Malaysia. So the floor is yours, Prof, and you have 15 minutes, please.
Okay, Assalamualaikum and good afternoon. I thought in Malaysia now is around almost 11 o'clock in the night. But anyway, first of all, I would like to say thank you very much to the organizer. Thank you for giving me an opportunity to share my thought in this lovely seminar. In this lovely seminar, I would like to give a talk on the title of the utilizations of CCUS concept in concrete technology. As mentioned by Dr. Wesam just now, I'm the Director for Institute Infrastructure Engineering and Sustainable Management in University of Technology Mara in Malaysia. This is one of the institute that are working on focus on the infrastructure engineering, and we are also looking on the sustainable management process, especially in the construction industries. As introduction to my presentations, as what have been mentioned by previous speakers just now, we have a critical issue when regarding to the cement. Both of the previous speakers are talking about construction materials, cement, concrete, and steel as well, but I'm focusing on cement, where we can see that cement are responsible to emissions of CO2. For every kilo of cement produced, 900 kilograms of CO2 was emitted to the environment. So due to this issue, the world organizations have come up with an idea to introduce a carbon CO2 tax. Okay, so when they are introducing the CO2 tax, all the industries who are producing the CO2 are getting worried because they have to pay for the CO2 that they have been produced. Due to that matters, an initiative to reduce the impact of carbon tax to the industries, they come out with another ideas. They call it CCUS. So what is CCUS is all about? CCUS is referred to what we call it carbon capture utilizations and storage. Okay, so the main reasons of having the CCUS instead of paying a high tax of CO2 tax, they may also working on the SDG requirement, and nowadays people are talking about ESG. So CCUS will become a greater point to the industry to get the ESG point and represent the initiative of SDG. So C is referred to capturing CO2 from industrial source. And then U is referred to utilizations of CO2 in concrete productions of occurring. And S is the storing of CO2 permanently in the concrete matrix. So before we talking about CCUS, I just want to give some ideas on what is happening to the concrete. Okay, previously we have the issue where in the concrete technology, during the hydration process, okay, it will produce the calcium silicate hydrate, and in the same time, the hydration process also will produce a calcium hydroxide. Okay, this calcium hydroxide was occurred in the platen phase, and unfortunately, the calcium hydroxide stopping the intersections of calcium silicate hydrate and create a micropause inside the concrete matrix or the cement matrix. So this issue have become a big worry to all the engineers and the scientists, and they are looking forward on how to reduce the compositions of calcium hydroxide in the cement matrix. So the concept of introducing CO2, okay, into the concrete is identified as one of the best method on how to overcome the issue of calcium hydroxide. Okay, from the research being carried out, it is identified that by introducing CO2 into the cement matrix, the CO2 has successfully transformed the calcium hydroxide to calcium carbonate. Okay, so the occurrences of calcium carbonate instead of calcium hydroxide has identified to reduce the impact of calcium hydroxide and in the same time reduce the impact of porosity due to the forming of calcium hydroxide before. So this is a great finding through the research being carried out. So what I can say here, the effort of injecting the CO2 during the construction process or during the hydrations of concrete or cement successfully reduce the issue of porosity inside the cement matrix, and in the same time helping the concrete industry and construction industry as well to um, reduce the impact of CO2 to the environment. So the industrial applications of CCUS in concrete can be applied by using it as a cement replacement material. We can use the carbon dioxide as an aggregate. We can use the carbon dioxide or the CCUS agenda as a gas additive. We can use the CCUS as the curing compound, and we also can use the carbon as the chemical solution. This slide shows that on how we are producing CO2, how we are producing an aggregates from the CO2. Okay, nowadays people in the construction industry are talking about RCA, recycled concrete aggregate. So actually this is one of the method on how to reduce the impact. Instead of using the natural aggregate, we might also using the recycled concrete aggregate. But somehow the recycled concrete aggregate have a problems due to the unquality aggregates, low strength of aggregates. And In order to overcome this issue, a research has been carried out by introducing CO2 to the recycled concrete aggregate. We are successfully transformed the calcium hydroxide into calcium carbonate in the recycled concrete aggregate and improve the properties of aggregate, such as the strength, the porosity, the water absorption level. Instead of that, we can also use a CO2 by injecting the CO2 directly into the fresh concrete. Okay, there is a few companies nowadays are introducing this technology to the concrete industry. By injecting the CO2 into the concrete, it is identified reducing the cement content. Okay, by where as I mentioned before, the chemical reactions, uh, the chemical reactions of transforming the calcium hydroxide into calcium carbonate, it has increased the strength, and the research being carried out by reducing the cement compound uh, and injecting the CO2 into it. They are successfully produce a comparative strength as 100% cement being used. Uh, Instead of that, it is also helping the industry in lowering the carbon footprint. This is one of the three methods on how they are injecting the CO2 into a concrete. We can inject the concrete, the CO2, either by introducing the CO2 into a water tank, and then the water tank being used in the as a water cement materials, okay, in the mix of concrete. Instead of that, they might also inject the CO2 into the water, and in the same time they are injecting and then they are actually they're making the what we call it, uh, cement slurry, okay, cement paste slurry, okay, where the cement paste been included into the water tank, and then these two materials been introduced to the aggregates in order to produce the concrete. Instead of that, we have the third method where the CO2 is directly injected to the concrete. Okay, so this is how we can utilize the CO2 in the concrete production. So the major issue to have to be identified is the total time of injecting a CO2 to the concrete. Because if we are injecting too much CO2 to the concrete, as we know that CO2 is an acidic gas, so and concrete is an alkaline materials. So when we are over injecting the CO2, the concrete will transform into acidic material, and there will no hydration process will be occurred. So this will be another issue. So we have to produce, or we have to identify the optimum time of injecting the optimum amount of CO2 to be injecting to the concrete. So this has become the challenge to the concrete industry, and it will become worse because the quality of CO2 have to be controlled. Okay, so because if you want to use the CO2, we have to make sure that we are using the same quality of CO2 in order to produce a higher or a better concrete strength. Instead of that, the CO2 also can be used during during the curing process of concrete. Okay, so we can use it especially in the precast industry, okay, or block pavers panels industry. Research have been carried out and identified that by curing the concrete with the CO2 at the right and optimum percentage and time, they will produce a better strength as compared to normal concrete. In UITM, we are producing a chemical called COS, or carbon oxide solutions, where the COS was produced at an optimum mixed proportions. So these chemicals was produced by injecting the CO2 into a specific solutions, and then we are using it as a water cement replacement. Okay, in the lab work that have been carried out, we are producing the three material. Actually, we are producing concrete, we are also producing bricks, and we are also producing blocks. All the material was being cast into a specific size, and then we are testing it, and we do identify that the utilization 50% of COS can be used and produce a better strength of concrete. So this is some of the methodology where we are producing the COS, and the COS being used as a water cement replacement in the concrete production. Okay, a result shows that the utilization of COS into the concrete, or the carbon dioxide solution into the concrete, somehow has reducing the workability of concrete. Okay, even the higher the carbon compound being used in the COS, the lower the workability will occur. So this has to be taken into an account during the design stage of concrete mix. But somehow the density of concrete was identified not really significant, being changed either by including the CO2 into the concrete. Okay, the difference is less than 10%. But this is the most important or the most interesting point. From the research being carried out, we are successfully increasing about 30% of concrete strength, okay, by introducing the COS into the mix. Okay, almost at all the percentage, we identify that the utilizations of COS has successfully increased or improve the properties of concrete strength, even though we are using the same amount of cement as compared to the control. On the fracture strength also, we identify that the utilizations of COS once again successfully improve the fracture strength of concrete. And then the permeability, the utilizations, as I mentioned before, the utilizations of carbon into the concrete will produce calcium carbonate, and the calcium carbonate will reduce the amount of porosity in concrete. The permeability result shows the reality of the theories. Okay, where we can see that the permeability value have been reduced as the utilizations of carbon dioxide in the concrete have been increased. Instead of that, we can also see that the water absorptions also been reduced as compared to the control specimen. So from all the research being carried out, what I can say that the with benefit of CCUS in concrete is especially is on the environment, where up to 15 to 25% CO2 reduction in concrete productions. The permanent carbon questions also become the benefit to the environment, because the CO2 have been successfully been cured or have been stored in the concrete. On the technical part, the utilizations of CO2 have increased the strength of concrete early and long term as well, reduce the permeability and improve the durability of concrete. Instead of that, if you're looking on the economic part, the utilizations of CO2 will give an impact to reduce the tax, the carbon tax. Okay, and then it also reduce the cement usage, and then faster the production cycles. So this will be a very good point when we're talking about the technicals. And on the economic part, we can see that the CCUS initiative has been so-called success, improving the concrete properties. But there's some challenges that we have to face, where the CO2 supply and the infrastructures to produce or to absorb the CO2 have to be seriously taken into account when we are dealing, or we are trying to use the CO2 inside the concrete industries. The process optimizations have to be identified, as mentioned before. The dosage, the pressure, the time, even the temperature also have to be identified and been controlled. And then there is lack of universal codes on the standardizations. As for now, there is no specific standard to represent the utilizations of CO2 in concrete. We are in Malaysia, we have Concrete Society Malaysia. I'm the ex-president of the Concrete Society Malaysia. We try our best to promote this product to the industry, and we also hope that the authority bodies will looking it as the serious matter in order to support the ESG and SDG initiative. Instead of that, as the long-term durability validations have to be carried out. Frankly speaking, the research being carried out in my lab. Up to this, we are successfully producing a data up to 1 year's data. But I do believe that this kind of research has to be carried out more and more. We hope that we can get more fund uh, from the industry and from the government as initiative and motivations to us in conducting the research for the futures. So I end up my presentations with the embrace change, lead the future. The world is shifting, and those who adapt and innovate will be the ones to lead the way. So with that point, I end up my presentations. Thank you very much.
Yeah, thank you so much, Prof, for your interesting presentation and findings. And now we move to the fourth speaker, Dr. Abdullah Faisal Al Sharif. And Dr. Abdullah, he is a senior lecturer at the University Tuan Hussein in Malaysia. So the floor is yours, Dr. Abdullah, and you have 15 minutes, please.
Okay, thank you. Can you share the slide?
Yes, sure.
And also you forget to mention that the CEO of International and Sustainable Research and Education Network.
Yeah, okay. Yeah, you can add that to the
Okay.
presentation.
Okay, can you share the presentation?
Yes, one second.
Okay, thank you to all, and thank you for Dr. Wissam for the invitation. And I would like to thank the organizer for this good seminar, and to all speakers. Today we are going to talk about the CO2 sequestration from different angle. We are going to using biosequestration. But before that, I would like to just to highlight about the sources, the problem of the CO2, and also what's the crisis, when the crisis happen in the world, what will happen to the CO2. I'm still waiting the slide.
Yes.
Okay. Okay. Can you move to the second slide? Okay. Okay. As we listen from the different speakers, they are talking about the CO2, the problem, and they highlight most of the what already involved in this infographic. I try to simplify everything to infographic slides. So if we go to the CO2 emission sources, we have different sources of CO2. We have the energy sources, which is the most, around 41%, transportation around 22%, as I can see also in the Dr. Faisal, what he mentioned. I think the sources and percentage is updated than mine. Its transportation is 29, and in mine is 22%, and also from residential and the other sources. Okay, why we are going to why we try to reduce the CO2? Because of the four most problem that occur according to the increase of CO2 is the global warming, climate change, and also the change in rainfall, and also the rise the rise of sea level. So as you can see in the picture, geological sequestration is the most used before to sequestrate CO2, and until now it's the most useful to sequestrate the highest amount of CO2 under the ground. But what's the problem? The problem is this way of geological sequestration is a very expensive, and also it's affect the ground and affect the soil. That's why many of the people around the world, especially the business people, they don't like to use it because it's expensive, and they want to I mean, the process, as you can see, the process of the CO2 sequestration from CO2 capture to compression and transportation, transport and injection in the soil. All these processes take a lot of money, a lot of time. That's why all the keynote speakers today, they are trying to find alternative way from the geological sequestration. Can we move to the second slide? The increase of CO2 concentration in atmosphere, if you can see from 1950 up to 2000, almost is still accepted. But what will happen from 1990 up to coming until 2100, it will be a high or double concentration of CO2. That's why we are trying to find solution from now. We are trying to find the solution for CO2 sequestration. Who is the responsible? The most countries responsible for CO2. All countries are responsible, but the most countries that the CO2 emission from is from China, United States, European Union, and India and Russia. Most of the keynote speakers already talk about the cement production, and they talk about the cement production because produce of 1 ton of cement is equal around 900 kilogram or almost 1 ton of CO2. Imagine 1 ton of CO2 equal to 1 ton, 1 ton of cement equal to 1 ton of CO2. Why China, the first one of CO2 emission? Of course, because of there is so many factories, but for your information, China is producing 57% of cement in the world. So more than half of the cement in the world that produced by China. And India is around 6.6% of producing of cement. That's why also India is 6% producing cement, CO2 emission in the atmosphere. That's why we have to look to the factories of cement, factories of the other factories also, but cement. I mean, if we at the first list, will list it at the first factories that produce high amount of cement. That's why we are trying to use alternative method to replace cement, or sometimes to reduce the cement. And some concrete now we are trying to avoid cement, but we cannot avoid cement to totally 100%. If we go to this presentation, we can see, okay, the second slide. Okay, we can see the crisis of in the world affecting the CO2 emission. If we can see the CO2 performance for the green depression is decreased, and when the second war occur is decreased, when the second oil shock is also decreased, the CO2. When the financial crisis happened in 2008, it's also the CO2 decreased. Also during COVID-19 in 2020, CO2 decreased. That means we are looking to the performance of the CO2, and the increase of CO2 in atmosphere is related to human activities. When the human activities is normal, of course the CO2 will be increased. So we are trying to find solution that can decrease CO2 and keep the life normal for the humanity. Okay, can we go to the second? To the next slide. Okay, this one I already talked about it, the sources of CO2 emission. Okay, now as Dr. Fazal talked, we are trying to use CO2 inside the concrete, but I will talk from different angle now. We are he is trying to injection the CO2 in the concrete. Actually, CO2 can absorb by concrete, or can be I mean, the concrete can according to the natural carbonation process, CO2 is sequestrated inside the concrete, but it takes a very long time to occur the carbonation process. After that, after we sequestrate CO2 inside the concrete, it will by chemical reaction, it will produce calcium carbonate. This method is naturally happened, but very, very slow. What we did in our research, we tried to use bacteria. We tried to use a bacteria inside the concrete. This bacteria, can we move to the, okay. Look at this infographic for the sources of CO2, all sources of CO2. Why we are trying to use concrete sequestration? Because concrete sequestration can sequestrate the CO2 from different sources, from the factories, from transportation, from residential, from energy, from other sources can be sequestrated inside the concrete. If we zoom the concrete brick, if we use the concrete brick and zoom a part of concrete, we can see the porosity. So if you see the foam concrete here, a lot of porosity. If we zoom the porosity, the pore, what we will find in the pore is some the void and calcium because of the cement. Now we are trying to use a new technology. We are using bacteria inside the concrete. What will bacteria, the mechanism, how the bacteria will work? Bacteria, if you can see the second void or the porous, it's using the bacteria. It's bacillus bacteria, which is looking like a banana. So what bacteria will do? Will produce calcium carbonate, produce enzyme, urease enzyme and carbon anhydrase enzyme. This enzyme are responsible to make a chemical reaction to absorb CO2 or to use the CO2 from atmosphere or from the concrete itself, and it will try to precipitate calcium carbonate around the bacteria, around the bacillus bacteria. So after that, this calcium carbonate will precipitate more and more until healing the pores of the concrete. Then the concrete will be self-healing. We call this process self-healing of the biofoam concrete. Can we move to the second slide? Okay, this is to make it more simple. I try to zoom this concrete pores and also using SEM image of bioconcrete symbol. And if you can see inside the pores, there is a bacteria. This bacteria, if we zoom it and try to explain the mechanism of this bacteria, how the bacteria work inside the concrete, it will produce the enzyme and the ammonia. This ammonia will be react with the bicarbonate. Actually, bicarbonate can be occur from the natural carbonation, but when bicarbonate meet the enzyme, urea enzyme and carbon anhydrase enzyme together, it will react with calcium and produce calcium carbonate. This process will do a self-healing for the concrete pores. It's also absorb CO2 from atmosphere and use the CO2 and to produce calcium carbonate, which make the concrete strength and also to reduce the permeability of the concrete. If we see to, if you look to the result, the concrete with bacteria, with bacillus bacteria or biofoam concrete is the initial water absorption. For the surface of the break, it's also produce self-healing already. The self-healing already occur. That means the result show that the penetration is reduced. So the water penetration is reduced for the specimen using bacteria inside the concrete. Also for this one, if we look to the carbonation with bacteria and without bacteria. Carbonation with the bacteria, but that show the bacteria is absorb CO2 and cause high depth of the carbonation. So that the carbonation, that's a proof that the bacteria with biofoam concrete is more than like using a normal foam concrete. That means CO2 already absorbed by CO2 by bacteria. Also, this one for the carbonation depth. Also, the carbonation depth, the results show that with bacteria is high compared to the carbonation depth with out bacteria. So some people will say if we use bacteria, so the carbonation will be uh, uh, more inside the concrete, which will affect the steel of the concrete. Of course, it will affect the steel of the concrete, but we are trying to use it for non-reinforcement concrete. Okay, look to the result of the CO2 with bacteria and without bacteria. If we can see the SEM photo with the out bacteria, how is the whole the porous is almost no precipitation of calcium carbonate. But in the other side, in the right side, with bacteria, we can see most of the pores or some of the pores already held by self-healing. This is we call it self-healing of the concrete for the concrete pores. In another hand, in another hand, by using EDX, we can see the calcium with the biofoam concrete compared to foam concrete is also already decreased. Why the calcium already decreased? Because bacteria already use the calcium of the which located in the cement to precipitate calcium carbonate. So when we do the EDX result, so calcium is reduced in the basement using biofoam concrete or using bacteria. Why? Because it's already used the calcium, some of the calcium in the concrete in producing calcium carbonate, which is the main role to produce to self-healing of the porosity. Okay, at the conclusion, we can see, if you can see the tree talking to us, that I can absorb 22 kg of CO2 a year, in a year. And the biofoam concrete can also reduce or to absorb 2.34 kilogram of CO2 a year. So each 1 kilogram, one metric cube of biofoam concrete can absorb or can sequestrate 2.34 kilogram of CO2. That means we are trying to, yes, the CO2 is emission from the cement factory, but in this research, we are trying to absorb the CO2 that emitted from the cement factory again to the cement, to the concrete. We are what's already emission from the cement, we are trying to retain it back to the cement again. Okay, that's all from my presentation. I'd like to thank you for listening, and thank you to all.
Thank you so much, Dr. Abdullah, for this enlightening presentation. And now we move to the last speaker for today, Dr. Ahmed Ghini. And Dr. Ahmed, he is the Director of the International Relations at Kumar University of Science and Technology in Sulaimaniya in Iraq. So the floor is yours, Dr. Ahmed.
Thank you so much for the introduction. I would love to have access to my presentation.
Yeah, I think I'll help you from here. Or can you do that from your side?
Okay, present.
Can you do the presentation from your side, or you need my help?
Yes, I'm doing it, I'm assuming. Yes, here it is. Is it clear?
Okay. Yes.
Is it clear? Yes, perfect.
Yes.
Hello, everyone, and thank you for having us, and thank you for listening to us. Thank you for the organizers, Dr. Wissam and Michelle, for this continuous effort towards sustainability. My presentation today, my subject today about the controlled low-strength materials. And today we will introduce alternative with zero embodied CO2 as a sustainable alternatives. So first, I would love to give a small introduction about what is the controlled low-strain material. So, and it is well known in the market by CLSM. It is, if we look at the case where we have excavation around pipes, around infrastructure, underground infrastructure, you have to have embankment and filling again, backfilling again from soil, and that soil required compaction, and you cannot do the compaction with a good consistency around all of those infrastructures because you are afraid of damaging them, and the placement as well cannot be easy. At the same time, you have a hazard of collapsing those things, as you can see here on the left, and that causes sometimes casualties or injuries. Our alternative is similar to a concrete. It's not a concrete. I will explain that in a bit. It is a slurry, self-compacting. It does not require any effort to compact it or place it, and it will provide a 100% capsulation around whatever we want to put in the under the ground. And not on the ground, we will come on other applications as well. So the idea, what is the requirement of it? As I told you, it is manufactured like a concrete, placed like a concrete, but it's behaved like a soil. Why I'm saying it behave like a soil? We will control the maximum strength that can reach to it in order to be able to do the excavation whenever we want. So the requirement, the first one is the flowability. It should be flowable according to the ACI recommendations, and it should provide capsulation within 1 hour, cover everything, and it gets hardened. And later, if I want to remove it, it will be easy for me to remove it like a soil, not like a concrete where it's be hardened. So the idea, if you look at the compressive strength development for the CLM, we all know due to the hydration process of the reaction in cement, you have your the strength of the cement increase with time, and you can see here the standard concrete. So you may, even if you decide not to exceed the excavatability limit, your concrete will get harder with time due to the continuous hydration. While the CLM, when they reach to the limit that we go, it goes plateau. The compressive strength of it goes like that. So normally they keep maintain a low strength, and that is under the control. That's why we call it controlled low strength material. So we intentionally control the highest strength can reach to it in order to be able to do the excavation later manually or with the same equipment that we use for soil. And the application of that, number one, the zone, the sewer line, the pipeline that we use, whether water or petroleum, other things, and the zone B under the pavement, we will replace that. We will replace those layers of subbase that we use, and with a continuous compaction layer after layer with the CLSM. And in many cases, we use it to take care of the underground void that was intentional or natural or man-made. When I'm talking natural, in some cases we have, due to the topography of the land, some areas need to be leveled. And when we add layers of soil, we have to do the compaction layer after layer. while adding this will be just set and give you the strength that you want. Or it is sometimes abandoned fuel tanks, void filling, whatever you have in building, you can do fill it with those material. Now, how come, what is our alternative, our proposal for today? The traditional CLSM used to use Portland cement and mined river sand in order to produce a low strength cement concrete to do this job. Our alternative today will focus on both of the binder and the filler as from a recycled or abandoned material that can be used to provide the main or the same goal or purpose that we are using. So in order for the binder, we will introduce similar to geopolymer, but we will use a material that never been used before for geopolymer because it cannot be worked for a real concrete. And I will touch base on that shortly. At the same time, rejected or off-spec cement that is rejected to due many reasons. I will explain that in the next slide. As a binder, in terms of the industry, in terms of the filler, we will use tailing, any leftover from mining here, and the industrial waste as well, to come up with the green, controlled, low strength material. Our replacement, as we said, the traditional Portland cement will be replaced by off-spec fly ash and off-spec cement. The virgin aggregate will be replaced with mine tailing, anything due to, those huge amount of volumes of soil or other related things that we have around mining when they, for example, for gold, for silver, for copper, when they get those, you will have mountains of leftover. We will use that as well. So whatever we have as a Portland cement, pure virgin mined sand and aggregate will be replaced with waste fillers and waste binder to get a zero embodied CO2 controlled low strength material. And when I say zero, because literally we will spend nothing in manufacturing them. So basically we will put zero CO2 during their manufacturing. Now, when I'm talking about binder, how is that different from geopolymer? Before, when we used geopolymer or the alkali activated material, we used the pure and standard fly ash, silica fume, or other things. But no matter where you are going, there is some stuff that cannot be used for concrete. One of them is bottom ash. Bottom ash is the part of the coal that was not burned even. So it's not transformed to fly ash. And pond ash. Pond ash is, if we go to the next slide over here, when they store or just deposit the fly ash, that is the leftover of it. And when it comes to the off-spec fly ash, there is type of fly ash that cannot pass to be using them pass the test and the standard due to lack of consistency or required chemical composition, physical composition, unburned material, all of that. Those are the stuff that there is no, till now, an application for them to be used with. On the other hand, we are repurposing the off-spec cement. Many times due to moisture, rain, or even the bad manufacturing process, we will end up with tons of cement that doesn't pass the standard test. So now you have to we are having a rejected, not allowed to be used cement. But because we are targeting a very low strength material, we can repurposing that, reusing this. And that can be used now in an application that I've just mentioned. In terms of the mine tailing, as I said, as much as they are spread around the mines, now we have an opportunity to solidify them in order to remove any possibility of creating this unwanted dust or the material that can go to the air. In terms of the circular economy, the beauty about this material, it can be even manufactured, not manufactured, inside the site. Means whenever we are demolishing or extracting, right away we are crushing those and directly use them in the mixer with a certain binder in order to use them again as a filler that can harden very fast. So this circulation of taking the unwanted demolished waste can directly transform to something useful. Now, when I'm talking about that, even for big cities where they are producing those solid waste coming from concrete, coming from brick, coming from all of those other products, can be right away processed to be put again in an application that required low strength material. And when you first cut the intensive use of the material that just my colleague mentioned, where the cement is responsible almost for 1 ton of cement, responsible for almost 1 ton of CO2 emission. So we don't have to bring those. We use what we have as a solid material, the solid waste, to recycle again. Now, another opportunity for those things is the encapsulation of industrial waste. We have some industrial waste that we wish we can encapsulate it in order to prevent any leakage from it and find a new purpose for it that create win-win situation. And for that, such a crushed glass or other type of sand that are not being used or wasted due to the certain manufacturing process, now that can be put together for a different purpose, which is improving using it for a useful purpose in construction, at the same time moving them from places that we don't like to have them in. Now, all of what I said, is it just an idea? The answer, no. That can be been examined. I was part of from a research group that worked on developing controlled low strength material, where we used mine tailing, bottom ash, and waste, where they literally passed every single checkpoint required by the ACI, American Concrete Institute 229 limits related to the flowability, the water demand, the early strength, and the ultimate strength. We got a very good result that qualify our proposed material to be used on the construction. Is what I'm saying come without challenges? We can use it right away? The answer, no. We still, based on the location, based on the waste that are using, based on the chemical composition of the material that we are using, we still have 3 challenges. Number 1, the water demand. some of the material, because they are very porous material, so they required a lot of water compared to soil. We have to do research in this matter and introduce, for example, air entraining admixture that give the flowability without water. The other thing, the gas expansion. We may, due to the chemistry or the chemical composition of those material, we may have a gas going outside a certain area. So we have to investigate our material and come up with our research that capsulate even the gas from those materials. And finally, the leaching. When I'm talking about leaching, is those material now I'm using under the ground during the water, the rain or stuff, they will not leach to the groundwater? The answer yes and no. If you do it in a right way, in a right mix, your leaching will be zero. But if you do it randomly, you may end up with polluting the groundwater with those chemicals. So that required, for example, trial mixes and requires strict pH monitoring to ensure the geopolymer matrix fully encapsulate any toxin. Are we fully encapsulating this or not? And most importantly, required more research in this area. Again, depend on the location of the material where you are. It may work for in United States, India, Middle East, and vice versa. Now, what we can get with this, a very beautiful, bright, sustainable future
Ahmed,
where we have
2 minutes.
yes,
Sir? 2 minutes.
yes,
2
I'm
minutes.
about to finish. Yes, where we have a sustainable future where we can have a zero material that required no compaction, no workers, no settlement, very strong enough to carry everything with zero embodied carbon in it. I will end what I am saying here. For years and years, concrete was the backbone of civilization. So concrete built civilizations. But now it must help to save those civilizations because it's come up now with a lot of CO2, a lot of carbon emission and dioxide come with it. So it's the time for concrete to be part from our green sustainable solutions. Thank you.
Yeah, thank you so much, Dr. Ahmed. Again, another interesting presentation and findings. So I'd like to thank all the speakers for these interesting sharings. And now I am moving the floor to Michelle to handle the Q&A session, to moderate the Q&A session.
Thank you, Dr. Wissam. Thank you so much for those presentations. And thank you to our audience for all of these questions. I know we're not going to get through all of them, so but we'll try to answer as many as possible. So I'll just ask for our speakers to try to keep your answer about down to 1 minute or so, if at all possible. I also want to just say thank you to our team. I know Hajra Jalil is out there, and we would not even be in this session if she did not warn me that we had some technical challenges. So thank you, Hajra, and thank you for asking all the questions and putting them in order. So we will jump straight into a question for Dr. Murugesh. And this question is from Abel Jimenez. And Abel asks, can this material formula be replicated around the world? What components are necessary that may need to be imported or transported to remote areas? And how will that increase the cost?
Actually, their question is based on whether the material will be get easily or not. It should be transportable or it should be a castable. So here I use as a hempcrete concrete is nothing but it's a sustainable material. We can go for any type of plants. We can go for aloe vera, we can go for water ice plant, or rice easily available material, rice husk, you can go there. Okay, so actually, what is the main concept is it is a fiber one. So whenever the fiber is adding to the concrete, it gives high strength and durability. So there is a concept we are adopted here. That's why we are using the sustainable materials we are using. As per their questions, whether it will be affected by water or any concept. So whenever the fiber is added to the concrete, automatically the porous get reduces when comparing to the conventional concrete. So whenever the porous is getting reduced, there is no chance for immersion or capability of water inside the concrete. So it will be increase automatically increase the fiber will increase the strength and also the durability. Next thing, the locally available we can utilize the local available materials. We should not transport anything. We have rice husk, so it is one of the material. We can have a sugar cane baggage ash. It is one of the available locally available. We can utilize our local available materials itself.
Thank you so very much. And for those of you who have not been with us before, there's a QR code for you to access your certificate, take the quiz, and also just give more information about yourself. So please click on the QR code. And our next question is for Ms. Shri. And this question is from Mohammed Tahir Zamani. And Mohammed asks, what are the primary sources of hidden CO2 emissions in the production of conventional steel and cement? And how do sustainable alternatives such as hempcrete and green concrete offer potential reductions?
Thanks, Michelle. Thank you for that question. Right, in conventional materials, a large portion of emissions is actually hidden in the process itself. For cement, the biggest source is calcination, where your limestone chemically releases CO2 along with high temperatures in the kiln fuel. And for steel, especially, I think emissions come from using coke to reduce the iron ore and the heavy fossil energy that's involved. Now, when we talk about sustainable alternatives, they address these aspects very differently. Like, for instance, we've got green concrete, which reduces emissions by lowering the clinker content and using alternative binders. This sort of, cuts a significant share of the process emissions itself. And on the other hand, when we talk about something like hempcrete, this goes one step further. Hemp actually absorbs CO2 while growing, and the material can even store carbon over time. So while traditional materials are inherently carbon intensive, you would definitely find alternatives which either reduce your emissions or actively remove carbon from the entire cycle itself.
Thank you so much, Ms. Shri. And our next question is for Professor Dr. Mohammed Fadil. And Zoraida Hussein asks, can green building certification and recycling practices be harmonized effectively to mitigate the environmental footprint of construction projects? And Professor, are you off of mute?
Oh, sorry. Okay, thank you, Michelle, and thank you to the questions. Related to the utilizations of recycled materials in the construction industry, yes, the recycle program nowadays has become an issue and has become an interest to the construction industry, especially when the governments or the organizations are giving an incentive to the constructions which use the recycled materials in their project. So by having the recycled materials such as the recycled concrete aggregate, we can reduce the impact of utilizations of natural materials. Instead of that, the recycling program also been used in the cement industry, where the waste from the identified uh, industries was studied and been used as a cement replacement material. Instead of that, the utilizations of waste material from selected industry also was identified, such as DGBS, can be used in the productions of geopolymer concrete and replacing 100% of cement, ordinary cement. So, by utilizing the recycled materials in the construction industry, we're talking about steel. People are using it as a steel, recycled steel. Timber also nowadays people are start working on the repair on the timber structures. So the all the harmonizations of the recycled materials in developing a green constructions can be what we call it can be used and give a direct positive impact to the environment. So thank you very much.
Thank you so much. And two quick questions. The first one is for Dr. Abdullah, and Hassan Al Marzouk asks, how many types of cement are there in the industry, and which ones of them produce the high amount of CO2 emissions?
You mean the type of cement is there are so many type of cement. We have Portland cement. We have cement that with high I mean using for high strength, and this different all the different type of cement produce a huge amount of CO2. I can see also in the some questions they ask, is it producing nine for 1 ton of cement 900 kilogram? Yes, it's produced 900 kilogram per 1 ton of cement. That's why all cement type are producing high amount of cement. The process of producing cement is produce high amount of cement. Even different type of cement, but the CO2 emission almost close to each other.
Thank you so much. Thank you. And we'll have one last question for Dr. Ahmed. And I know that we have a lot of other questions that have been asked, and those will be addressed by our speakers after the program has gone live. So that's why we always ask that you put the name of the speaker for whom you're asking the question. So Dr. Ahmed Nur Adila Latif is asking, since materials like hempcrete require a secondary structural frame and significantly longer drying times, how do we ensure that the additional carbon from transport labor and extended site logistics don't cancel out the embodied carbon savings of material left?
Very good point. Number one, I am not manufacturing any material for this purpose. Literally, most of the time, not most of the time, all of the time, I'm using abandoned material that has no embodied energy put on them intentionally. So I'm finding a new home for those things related to the curing and the process that I'm talking about. It's comparing, I showed that in my first slide, compared to the worker, the compaction, the transportation that I'm using for soil with compaction. I'm introducing something that does not need any worker, does not need any compaction, and basically use material that are abandoned for both binders and filler. So definitely, if I am comparing myself to a virgin material that required work to be done, I am definitely making the plus in terms of reducing the embodied energy in that regard.
Brilliant answers. Thank you so very much. Thank you again to our speakers. Thank you for our audience for asking such insightful and well-educated questions, and also providing comments, sharing where you're located. I will pass it back to Dr. Wissam. And I also would just want to say thank you again for your patience today. We've never had a technical glitch like we've had today. So it's just been so inspiring for all of you to still be with us. And Dr. Wissam.
Yeah, thank you so much, Michelle. And thanks to the speakers and for the audience. Again, very interesting and fruitful discussion, even though it's a quite technical topic, but it's very relevant to the global scenario. So yeah, I would like to thank you again, for your patience, and we made it successfully, and we'll see you next week in the fourth module, and we'll have a lineup of speakers, experts in the field. So we'll be looking forward to see you all next week again to continue this interesting program. So have a good time, everyone. Thank you so much. Bye bye.
Thank you.